Good. So welcome back, everybody. Now we move on into our, I believe this is lecture 7, where Nico is gonna present the gravitational wave module, which allows in CosmoLattice, well, he's gonna present the theory in general of gravitational waves creation and propagation, and I guess he will comment to some extent how this is implemented, the technique in CosmoLattice, preparing you towards the practical session tomorrow, which will be about gravitational waves. Okay. So, Nico, the stage is yours. Please go ahead.
Okay, so welcome back, everybody. So this lecture, as Danny said, will be about the gravitational wave module, how to study dynamics of gravitational waves in CosmoLattice, which will have a theoretical section, and then how is it implemented in CosmoLattice and in general gravitational waves in the lattice. So this work was done. These slides were work on collaboration with Jorge Ballesteros, that you know already him. So let's go. These lectures are based on, this lecture is based on 2 technical notes that are available on the webpage of CosmoLattice, technical notes 2 and 3 on gravitational waves and gravitational waves from U1 gauge theories, which if you go to the, or you already know where the CosmoLattice webpage is, you go to documentation, technical notes, and you will see there are 3 of them. And basically this lecture is based on these 2. So let's jump into the theoretical basis of gravitational waves. So what are gravitational waves? Basically what they are is they are tensor perturbations of the flat FLW metric that we're considering. So if we take the flat FLW metric and we consider perturbations to the spatial component of it, these perturbations will have the characteristic of being transverse, which is this condition here, and traceless. So if we work out equations of motion in the linearized equations of motion of these tensor perturbations, we will find that they follow a wave equation. You can tell from this form, this is a wave equation in a very similar manner to the Klein-Gordon equation in the expanding background, which it can be told by the friction term here, which is sourced by this object here that I will tell you what it is later, but you can see the tensor perturbations of the spatial component of the tensor perturbations of the metric have a equation which is a wave-like equation. So just to set the ground, I and j here, the Latin indices are meant to spatial components, and summation over repeated indices is implied. So let's go to the equation again. And as I tell you, this equation is sourced by the transverse traceless part of the anisotropic stress tensor. So, and this means that the conditions of being transverse as traceless should be held for every position and every time. And what is this a problem? Because having the transverse traceless part of an object of a tensor in real space is a non-local operation, which is a problem, but I will tell you why. An easy way of getting the transverse traceless part of an object is going to Fourier space. So here I show you the continuum, the definition of a continuum Fourier transform for, in this case, a scalar field or a function. And once you have the Fourier transform of your object, in this case the tensor, you can just apply this projector, which is defined here, and where P, as you can see, is defined here. In this case, K means the momenta, and the K hat are unitary momenta normalized by the modulus of this vector. And if you construct this projector in Fourier transform and you apply to this tensor, you will get the transverse traceless part in Fourier space. Okay, so you can check yourself that if you apply this projector to this tensor, it will satisfy the conditions of being transverse and traceless. And now, if we did that, we Fourier transform first or anisotropic stress tensor in real space. Then we transform it, we project it to transverse traceless space. And then we want to get it back again into real space, we will need to make a Fourier transform, a backwards Fourier transform. And this is a problem, as you can see. We are doing two non-local operations. We are getting the Fourier transform first, projecting, and then Fourier transform it back to real space. This is very costly, and this will be a problem when we want to follow the dynamics and solve actually the equation of motion of the gravitational waves. But let's talk a little bit about what the source is, which I told you is the anisotropic stress tensor. So basically is the deviation of the energy momentum tensor from being a perfect fluid. If we just consider the special part of it is the energy momentum tensor minus the homogeneous background pressure multiplied by the spatial component of the metric, which is given by this. So basically is the deviation of the energy momentum tensor from being a perfect fluid. This will be our source of gravitational waves. For example, if we have just scalar fields, this will be like as easy as this, well, as easy as taking the transverse traceless part of it, but it's just the gradient of the fields in the ij directions and the product of them. So this will be the anisotropic part of it. And then we have to take the transverse traceless part of it to source into our equation of gravitational waves. Okay, so now let's talk about which observables do we care about gravitational waves. So we can consider, we can take this equation here, which is the energy density of gravitational waves, where basically is the byproduct of the time derivative of the transverse traceless tensors, the hij here. And this is averaged over a volume such that, this is important, this is valid only if the volume we are considering or we are averaging over is contains all the relevant wavelengths. So that means it's large enough, the volume, such that all relevant wavelengths or the excitations of these tensors are well inside the volume we are considering. So if we are here in real space, we can now go to Fourier space, and this will be approximate to this, because again, this jump is valid only when we consider large enough volume such that our wavelengths are inside of this volume. And we can define the energy density per logarithmic interval, and we can write it in this form, which we'll see that it will be useful for us later. So here I show you energy density per logarithmic interval. This is the observable that we will compute, that we will help us to follow the dynamics of gravitational waves. But also, we know that in the early universe, the source of gravitational waves have a certain stochastic nature. So they are produced everywhere, and what we measure are like different realizations of this background. So instead of computing an average over a volume, we can consider actually an ensemble average over different realizations of the stochastic background. And this is what I do here. I am now, instead of taking a volume average, I am taking an ensemble average of this 2-point function. So now, instead of considering the product, now I'm taking the 2-point function of the gravitational wave modes here. And here I am using isotropy and homogeneity, such that I say that the power spectrum of the time derivative of the tensor modes is defined like this, in this form, from the 2-point function of the gravitational waves. And again, I can replace back into my definition of the energy density of gravitational waves, and I can write down the energy density of gravitational waves as the integral over the power spectrum of the time derivative of the H tensors. So again, I can write down the energy density per logarithmic interval in this manner. So this is the observable that we will care about and we will compute to follow the dynamics and the production of gravitational waves. Furthermore, we also like to write down the gravitational wave energy density as normalized per the critical energy density. So here the critical energy density, you all know how is it defined. So if I do this, I define the omega GW, that is this number that you will find everywhere when somebody talks about the production of gravitational waves in the early universe, which is gravitational wave energy density per critical energy density, defined as here. So remember this equation, that's the equation that we would like to compute from the lattice. So as I told you again, let's address this problem now. So let's imagine that we are able to solve and follow the dynamics of the gravitational wave equation, but we need to do this non-local operation every time step. So this is a problem. This is very costly. We need to do 2 Fourier transforms every time step. We want to get the transverse trace part of the anisotropic stress tensor. So how do we solve this? Here, I told you, I say again, every time step we need to get this. So how do we solve it? Non-local operations are computationally expensive. Having to compute 2 Fourier transforms every time step is prohibited. So what we do instead of that is, let's actually evolve a set of unphysical tensor modes, what I call them U, and let's evolve this equation of motion. Now, you already know how to do this. This is basically U are 6 degrees of freedom, because IJ, these are symmetric tensors. We have 6 degrees of freedom to evolve, following a very similar equation than a scalar, than the Klein-Gordon equation for scalars, sourced by this now the anisotropic stress tensor without doing the transverse trace part. So now this is just product of the gradients of the scalar fields, for example. And whenever we need to compute an observable of the gravitational waves, in this case, the power spectrum of energy density, we go to Fourier space, we apply the projection, and then we compute of observable. So why this works? Why this works? Because basically these two operations are linear in Fourier space. So I have my projection of my U fields. This is how my U fields I define it. This is basically the projection using the lambda projector that I defined before. Applying over my U fields, I will get my H fields, my transverse traceless tensors. This is the equation of motion, let's say, in Fourier space. So I have my equation here, sourced by the transverse traceless part of the anisotropic stress tensor. So now I rewrite this as using my projectors, and I see that these two operations commute. So I can just put it at the beginning, and then say I evolve my U fields sourced by the very easy form of the anisotropic stress tensor, and then whenever I need to compute an observable, I transform it to Fourier, project it to transverse trace part, and compute my observable. So every time step I evolve a simple equation for 6 degrees of freedom, and few times whenever I need it, I actually get my transverse traceless part of the tensors. So let's remember again, this is what I want to compute, which is the energy density per logarithmic interval, you know. Here I have my transverse traceless tensors, which you know how to get them every time we need it. Let's rewrite this in function of the U fields, the ones that I actually evolve. Here I am using a property of these projectors lambda, which basically they are idempotent, which means that if I apply 2 times the projector, it remains the same because it's a projector. That's a property of a projector. Here is the property there. And actually, I can rewrite this because as you can see, I am contracting the indices I, j, j. Basically, this is like taking a trace over matrices, and I can rewrite the product of the transverse traceless tensors now just as a function of the U fields, the ones that are I evolve, and the projector speed. And this is a very easy equation. So this means that whenever we want to compute this product, we just need to compute this expression here from the U's that I am evolving. And I am remind you again what P are, which is here, the transverse projector. And furthermore, I can just express this in this manner, which will be easy to implement. I do this just because it is easy to implement in the lattice and it's easy to see it. That if I define the product of the projector with the U tensors in this manner, and I also define this tilde, I can write the trace of this product of 4 matrices in this manner, and the trace of the product of these 2 matrices in this manner. You see, I am reducing, so I don't need to actually compute the full projector and then taking the trace. I can just write it down directly. I don't need to do any matrix multiplication. I just write down directly what will be the trace of this matrix multiplication. And just to notice that actually the complex conjugate of this B tensors, let's call it, are equal to the tilde tensor that I am calling here in the continuum. This is because the projector P in the continuum is real value, but in the lattice this is not the case, and I will show you later this why. So let's change a little bit. So I will now talk about gravitational waves in the lattice, but if there is any question up to this point, I can answer them. Is there any question about gravitational waves in general? No.
Everybody has cleared this trick of commutation at the linear level in Fourier space and why we do it like that?
Yes, looks like.
From the silence,
okay.
It's not clear.
In the chat, there is no questions. Okay. So let's now talk about how gravitational waves are implemented in the lattice. So I already told you a lot of times about this, but maybe let's remember a little bit what is the lattice. Basically, it's a periodic, it's just a set of points that are periodically spaced by a dx, and we can actually define every lattice site as a position with this position vector, and it goes from 0 to n minus 1, which is n is the number of points per dimension. If we go to Fourier space, we also have we get a discrete lattice, but in this case it goes from minus n halves to plus n halves, and the length of the lattice of the reciprocal lattice now is given by this expression, and the minimum, well, not the length, but the minimum momenta that we can resolve in our lattice is given by this expression, and then also we can compute what will be the maximum moment in the lattice, but this has been already explained several times. We can also define Fourier transforms in the lattice in a very similar manner, but instead of taking integrals over all real space, over all Fourier space, we are actually adding over lattice sites in both lattices. And now we can also define a lattice momentum. So this is where I told you that the projection Fourier space is not necessarily real value in the lattice. Why? Because we can define a lattice momentum for a given choice of lattice derivative. So if I apply this lattice, this derivative operator to a function in the reciprocal space, I can define my lattice momentum in this way. So for certain choices of discretizations of the derivatives, I will get different lattice momentum. So for example, if I choose my derivative such that is center in the lattice site, so I'm just taking finite differences between nearest neighbors, my lattice derivative, my lattice momenta will be real valued. But if instead of that I choose the forward or backward derivative, my lattice momentum now is complex because of the phase here. And now this will actually, this is important to notice, because this will change several properties of our projectors that we cannot just extrapolate from the continuum. We need to work on which properties of the projectors, or actually how to write down the projector properly in the lattice, such that we achieve, whenever we apply these projectors, we get the transverse traces part of the tensors that we want. So if I write down again the equation of the physical degrees of freedom used in Fourier space, it will look like this. Now, as you see, I am writing the source as the full anisotropic stress tensor, and the use here. Whenever I need, I will project them by using the lattice projector. That's why I am now putting this subscript L here, because it's not the same as the continuum. And for example, if I haven't choose any lattice derivative yet, but the definitions of them will be something like this. But let's actually specialize to every choice of lattice derivative. So just if you want to check, there is this reference where there is a discussion about this. So for example, if I choose a forward-backward derivative that leads to a complex value lattice momenta, I have these properties. For example, I have the property of being transverse, but it's not true when these two indices are interchanged. This is not zero anymore, and it's the same here. So now this is, so it's basically when I interchange an index here, I need to actually consider the complex conjugate of my lattice moment. The same here. My lattice, my projector, it cannot be symmetric anymore. It's actually Hermitian. So I need to take the complex conjugate here such that this is true. And for example, for a real projector, this won't be the case, because again, for a real projector, the complex conjugate is the same as the number. So these properties here are the same, especially this one, which is again the idempotency. But as you can notice, for the complex projector one, we have certain issues that we should address. So again, we want to compute the energy density of gravitational waves. We will consider the volume average over this byproduct of gravitation of the transverse traces tensors H. In the lattice, this looks like this. I am just adding over all possible lattice sites in the real space and taking the average of it. But I can do the same in Fourier space. Actually, I want to do this in Fourier space because for me it's easier to get this in Fourier space, the Hij tensors. So I do this in Fourier space, and I will now start explaining how we do this in the lattice. So we take our Fourier space, and we can break this sum over all lattice sites into two sums. One over moment, let's call this, this is the modulus of n. So we are taking circles or shells over the Fourier space. And then here means a summation over all points that are within this shell. So for example, the blue one here, the green one here, or the red one here. So I just break my summation in adding over circles and then adding over points lying in the circle. So I can split my sum here. So I can rewrite my sum here over points lying between these shells by doing this. So I am saying I can write down the same addition as the average over this product over the shell times the guess I can make of how many points are there within these two circles here. And educated guess, let's say, will be that there will be a number equal to this, which is basically the surface of that circle, of that sphere. This is an approximation, actually, because I am guessing how many points will be in this between these two spheres. But this is not the real number of points that are there. I am guessing the multiplicity of each shell. But this allows me to write in this manner because as you remember, how we wanted to write this was the energy density of gravitational waves per logarithmic interval. So it's like we want to split my product in Fourier space into shells and then add them and then taking the logarithmic interval of each one. So I can just rewrite what I did here into this manner. I take this d log, so it's just to put into a similar manner of how I defined the gravitational wave power spectrum before. I want to recast what I do in the lattice into that form. Okay. So if I just make the parallel, I just compare what I did in the lattice to the expression that I show you in the continuum, I can argue that what I call the logarithmic interval of gravitational wave energy density power spectrum is what is written here. Okay. And I just need to get this product for the H tensors, the transverse traces part of them. So I know that if I am evolving the use, I just need to compute this expression here, which is product of matrices and taking the trace of it. And I have everything done to compute the power spectrum of gravitational wave energy density. So we just need to compute that. And I can normalize by my critical energy density and I get the omega, which is the observable I want to extract from the lattice. So again, is there any question up to this point? Especially regarding how to compute the power spectrum? I think this was already explained before. Yep, no. Any feedback? Is people there? Hello.
Yes, we can hear you.
Yeah, so I mean, so is there any question up to this point? No. Okay, so maybe now I can jump into how we.
Nico, there
No.
is a question, I think, by Alex Bigman.
Okay. It only, yeah. So yeah, it actually, we do that. We only take in consideration the kinetic energy of the gravitational wave. So we start from this definition, which is what you will encounter everywhere, how to compute energy density of gravitational waves. Most of it will go into the kinetic energy of them. So yes, we only consider this part.
Well, yeah, but let me comment on this. It's not that we consider,
Yeah, maybe.
And we are missing another part. The energy density ascribed to tensor perturbations in an expanding background for freely propagating waves at sub-horizon scales is exactly this expression that boils down to the kinetic term. In reality, you could think of extra terms. For instance, there is the gradient term, but for freely propagating gravitational waves, this boils to the same expression, except that each of them has a factor 1/2. You add them up, you remove the factor 1/2, and this gives the final 1/32 pi g here for the kinetic term. So for sub-horizon scales, this is fine. And of course, you know, here we are sourcing the gravitational waves, but eventually you end sourcing them, and this is what you are propagating. So that's why we only care about the kinetic term, because it really represents the full spectrum of the energy density carried by a stochastic background of gravitational waves at sub-horizon scales. Yeah. There's another question.
So it says the anisotropic tensor depends on the gradients of the scalar fields. So what is the gauge choice in CosmoLattice to evolve the scalar fields? Maybe you can answer this question,
Yeah,
Danny?
there is no gauge choice for singlet scalars, which is the case Nico is discussing, okay?
Yeah.
There are gauge choices for gauge theories. So essentially, when have you prepared something on gauge theories as well, Nico? Sorry.
So there is, I mean, I will.
No, sorry. I just mean the evolution gauge. So it's like the comoving gauge or the synchronous gauge or
the tensor. No, sorry, I still don't understand. These are the gradients of the scalar fields. There is no gauge involved. Okay. And then we are following the tensor modes, which are gauge invariant in the diff. How is it called? Sorry, the perturbative diff transformations.
His question, I think, question is, can I?
So let me first, you know, clarify this with Christian. Okay, so there is no gauge choice involved here in what we are doing as of this point. Is that clear?
Yes. I was thinking more in the evolution of time. So what's basically when you split the space and time, you have a lapse and the shift. That's at least when you do full numerical relativity. But now you're already doing lattice. But I think you still have to specify how your coordinates evolve, right?
No.
Cosmological
perturbation theory, an alternative way to do the approach is to decompose all your perturbations on top of a Friedmann-Lemaitre-Robertson-Walker background as scalar vectors and tensors. Okay, and here we are only following tensors, which are by default gauge invariant. And
yes, the tensor, yes.
And that's why they represent gravitational waves, actually, you know, the true degrees of freedom propagating in gravity. And there is no gauge to fix in terms of the other guys, you know, because yeah, no. If you want, the scalar fields are already yeah, they are singlets, you know. So I'm not sure how else to describe it.
Maybe your question is about the evolution of gauge fields, because okay, we also consider the production of gravitational waves due to the gauge fields. So I think for the evolution of gauge fields, we are choosing a gauge, right?
Yeah,
Yes.
I think I was confused because I was thinking that yes, of course, the gravitational waves are gauge invariant, so you can go, so they are invariant in whatever gauge you choose. However, you are evolving them, I think, using the gradients of the scalar fields, and for example, you could choose a gauge where basically the scalar field is uniform, is basically constant, I guess. But
No, because the scalar fields are not gradients of the is not the perturbation here. You know, this is the fully nonlinear. Okay, you cannot take a gauge choice of coordinates where I adapt myself to the shape of the gradients of the scalars. This is not what you should do. Here you are taking that the universe is homogeneous and isotropic, so spherically isotropic. This is what allows you to do the composition into scalar vector tensors in first place, okay, in cosmological perturbation theory. And you are assuming this cosmological principle in the statistical sense. Okay, so that in the large scales, much larger than the wavelengths we are representing here, then statistically you are preserving this isotropy. You see?
Okay.
So I understand what you're saying now. Okay, I understand, because if you wanted to follow locally space-time, then I wouldn't be in Friedmann-Lemaitre, Rosen-Walker locally where I have the gradients, you see? But the whole point of this is like in large scale structure, is to understand that what you do locally does not affect what you are doing globally in the expansion of the universe. You see? However, what you do locally affects the gravitational wave emission. And that's why we follow locally the gradients.
Yeah.
Okay, so we are separating the background with a different scale, which is the homogeneity scale, and then the local nonlinear dynamics that are sourcing gravitational waves locally.
I see.
It's a standard approach, but feel free to let me know later on if you want to discuss it more, of course.
Okay, thank you.
Yeah. There is another question from Alfredo. Nico, if you want to take it.
Yes.
So yes, I have a same question. I had a same question. Yes, I got the answer actually.
Okay. So we also have a type 1 and type 2 power spectrum for gravitational waves in CosmoLattice. Yes. So yeah, it's the same approach as we did for the power spectrum of scalar fields. That as I told you here, when we split this summation, you can actually, instead of guessing the number of points that are in the shell, you actually put and count them and use them to make this break of the summation. And that will mean that for gravitational wave spectrum, we also have the power spectrum type 1 and type 2. And I will show you how the final expression looks like later. Yes, we do have that. Was that the question? That was the question, right? Yes. Okay.
Another question by Isaac, Nico, if you want to take it.
Yeah, okay, thanks. So it's a very quick one. So I wonder, is there any reason at all to actually not use the explicit counting of the number of modes per shell and just use 4 pi? Because I don't see why you would ever use, well, actually not count them.
So is there any reason why we do this, the multiplicity?
Yeah, instead of just actually counting the number of modes per shell, because
it was like just to make like some parallel kind of thinking with the continuum. So in the continuum, when you split this integral, you can actually do that. Just take the average of this product over spheres, surface of a sphere. And it was just that. It was just to try to do the same as we do in the continuum. But of course, this fails.
In practice, when you run this, you always choose the more exact method where you just count the number of.
You can choose both. That's the thing.
Okay.
No,
But yeah, in principle, the one that is being by default is the one that you count explicitly the number of on points on each shell.
yeah,
Yes.
but this is still a good question. The point is, Isaac, we are telling you the whole story a posteriori of how things were developed, But
I see.
when people started to develop these things, initially we were making these mistakes of approximating this one way or another. And it turns out that historically there is a bunch of a lot of papers that are computing the gravitational wave spectrum with the 4π counting, So if you want to do comparisons, then you need the 4π, and this is why we provide it, just for the sake of comparison.
In the previous, yes.
So this is more like an historical artifact, which for the sake of comparison is still lingering.
I would say so. It has no really, how to say, particular value nowadays. Nowadays people could have realized about this long time ago. But the thing is, when people develop things, you always build up these kind of things until you realize you can do better. Okay, and in the case of spectrum gravitational waves, for many years, I'm afraid many papers have the 2π counting, because we were just thinking how to, as Nico said, how to mimic the continuum. You were thinking in the 4π solid angle, But I think it's good to have it just in case you want to double check with previous calculations. Otherwise, of course, you should stick in principle to type 1 because, as I said, that's more accurate given the lattice limitation.
But okay, so also on this note, instead of actually dividing into bins, an even more accurate way would just to uniquely identify. If you just take the momentum squared, you will get a unique integer, right? So in principle, instead of dividing into bins in the first place, you can just identify each mode with the square of the momentum and just average over those modes that have exactly the same.
Yes, the problem of that, there are two problems of doing that. You can do that, and in lattice QCD, people do it when they want to do the most exact lattice representation of a spectrum. Okay. What's the problem? That there are two problems. If you do it like that, when you plot your power spectrum, the different k values are going to be very irregular because you go sampling a three-dimensional space, and which momenta you go fitting are really irregular. They are not jumped by unit intervals of k infrared. That's one problem. It's not very relevant, but it makes more difficult visualization sometimes. But the second problem is that if you do it like that, you're going to find a number of momenta that is very poorly statistically sampled because there are few representations of them, that happen to have that length. And of course, that problem is ameliorated the larger the k, but that problem is it adds to make the spectrum much more noisy than what you really want to represent, because what you really want to represent is the statistical average of modes that have the same wavelength. And by doing this binning, what you do is you approximate all the modes within a given bin by if they were having almost the same momentum length, radius. And you have a better statistical sampling in that way, So at the end, it's a compromise. What you want to do, it's a choice. It's a choice because the space is discrete, and you have to live with the limitation, and hence how you want to imitate the continuum. I personally prefer the binning because of this reason. It has a better fair statistical sampling for a given radii of momenta, which of course is uncertain because there is a given width associated to what is the radius of momentum for which the power spectrum is being computed.
Yeah, okay. Thank you.
Okay, so there is one comment on the chat that it says that counting the points is computationally a headache and doesn't make much difference, but okay, let's it makes difference between this approximation, especially for the smaller k bins, like the first bins, let's say. It actually this estimation overestimates the number of points, like for 30%, something like that, for the first bins, and then for the bins that are outside of what it's called the Nyquist cutoff, which is when we consider a shell which with a radius larger than half of the length of the cube. It overestimates the number of points for a considerable factor. So, and actually the counting of modes, it was done already. It's implemented in CosmoLattice, and it's better to use it. So maybe we can just stick to the way of computing the power spectrum by actually considering the actual number of points in each shell, because it actually matters, especially for the most UV beings.
There is a question by Alessio, I believe, or he's just with his mic out. Okay, no.
Okay, so now I will.
Nico, you've been like over 45 minutes. Do you want
Okay.
to take a break now? 5 minutes?
Yeah,
break?
we can take a break now. Yes.
Excellent. We'll be back in 5 minutes. If there are more questions to Nico or to any of us, we are happy to take them, of course. Shall we start back, Nico, or we wait something more? A bit more. You are muted. You're still muted.
Yes, I am now. Yeah, we can restart.
Okay, then let's continue. Go ahead, please.
Okay, so let's go to the last part of this lecture, which will be about how gravitational waves are actually implemented in CosmoLattice. So I will give you like all where to dig into the code, so you can check how the gravitational waves are being implemented. So let's start by, of course, defining what the program variables are. You already know all of this. And I am adding here also that we will now consider the gauge fields, the vector fields, that we will be also another source of gravitational waves, and I will show you how is it source. So just to explain a little bit how is it done, as I told you already, we actually evolve a set of fields, actually 6 fields, these U fields, and we just follow the same prescription as if they are scalar fields. So they follow the same prescription by defining the conjugate momentum in this way. So I am able to write down the evolution equation for the amplitude and for the conjugate momenta, where now we have what we call the kernels. We have it here. And this is where the source of rotational waves will go. This is where my product of gradients of scalar fields or all the other expressions will go. And I will show you explicitly what we do. In CosmoLattice, we actually define our U fields in this manner. So we multiply them by this factor. It's just such that we absorb into the definition of the U fields all these factors that will go here if we wouldn't do that. It's just in order to, whenever we evolve the fields, we have all these numbers here without any exterior factor, let's say. That's why we do this definition, but we actually should take care about how we define our U fields, because it will actually matter when we compute energy density. But this is just a choice, such that we don't see this factor here. That's all. And here is the full anisotropic stress energy tensor that we actually compute in CosmoLattice to follow the gravitational waves produced by real scalar fields, that basically the source of them are product of the gradients in the ij directions, and we add over all possible scalar fields complex scalar fields that are charged under a U1 gauge charge, and that's why when we compute the source of this complex scalar field for gravitational waves, we need to take in consideration 2 times the real part of this product, where these are actually the covariant derivatives of the complex scalar fields under the U1 gauge field that I am defining here. And here is the source of gravitational waves by the vector fields, and they are sourced by products of the electric and magnetic field, with these factors here of the scale factor that are very important. And because of the way how we measure of vector fields, we measure in units of omega star. And you remember that we measure of fields in unit of F star. We have actually to make a choice on how do we want to measure of, in which units we want to measure the anisotropic stress tensor. And just because at the beginning, we just had scalar fields, which are measuring F star units, and derivatives, which are measuring omega star units, we just said from the beginning that we want to measure, there was a choice, we want to measure the anisotropic stress tensor in units of omega star F star. And that's why we have this extra factor here. It's just to take into consideration that vector fields are measuring omega star units, and scalar fields are measuring F star units. And this is very important. I mean, you shouldn't forget about this. It's super important to be sure in which units you are measuring each field. And this is a full tensor that we are measuring in CosmoLattice to follow the dynamics of gravitational waves as sourced by these fields. So, how is it implemented and how it is being coded into CosmoLattice? For that, we will look into several files a little bit. I'm not just showing you all the code, but the key parts that you want to look and show you how it's done. So the first thing that you should care about is how to actually tell CosmoLattice to evolve gravitational waves. And this is very easy done in CosmoLattice. You just need to add a line into the parameters file. Let's say we want to do lambda phi to the 4. You will just add into the parameters file this parameter and set the flag to true. And this will be everything you need to do in order to evolve and to consider the evolution of gravitational waves in CosmoLattice as being sourced by, for example, a lambda phi to the 4 theory. And this flag here, I will explain you later what it is, but you may already know what I told you. The type of projector we use to compute the projector of the TT components, the projection of the TT components depends on our choice of lattice derivative. So in principle, if we choose the forward-backward derivative, the projector will take into account that and will choose lattice momenta, a real value 1 or a complex value 1. And this is where you choose that. But I will show you which one of these numbers refer to which kind of projector. So if you want to project your gravitational waves using a neutral derivative, that means a real value projector, you will set to 1. If you want to do for forward derivatives, you will set to 2, or for backward derivatives, you will set to 3. And the default value, that means if you just set gravitational waves equal to true, and you don't add any parameter regarding the projector type, it will by default use the forward derivative. There are actually a difference by using these two, especially the neutral compared to the forward and backward derivative. There are a difference, but they are very mild, and we will show you this tomorrow. But for the time being, let's say that we just set it to 2. So when we have our results done, the gravitational wave module produces two kinds of files. The spectra GWS file, which in a similar manner as the spectra of power spectrum of scalar fields or the matter fields, you will have 3 columns. The one that accounts for the momentum of the beam and the value of the gravitational wave energy density per normalized per critical energy density for each one of the beams and the multiplicity of the beams. So this is what we measure goes here. And you have another file that it's called energy GWS, which actually it takes the integral for each time that the power spectrum is being computed. It integrates over all possible available momenta, and it plots or writes down 2 different values. The one for the normalized gravitational wave energy density per total energy density of the matter field, and the one that is the full, just the gravitational wave energy density as measured in these units. But the one that we are going to care most about are the one normalized by critical energy density.
Let me make a comment, Nico. I think important to highlight that these ratios are at the time of production, what Nico is showing.
Yes.
So even if it's the critical energy density in the given scenario, it is at the time of production, which means if you want to translate this into a prediction today, you need to redshift both amplitude and wavelengths, okay? Knowing your posterior history to the end of production of gravitational waves.
Okay, but yeah, just to what we do usually is take the last spectra, and then from there we redshift. And there is a question in the chat that it's what is the multiplicity parameter? Is basically the number of points that are within this bin. That we are just showing you that it's basically, you say that it's difficult to count the multiplicity of the bins. No, what we actually show what is that. But yeah, this is not a physical parameter, it's just a lattice parameter that we display there. It says production meaning at the time of re-entry. No, because these fluctuations do not leave the horizon, no? These are being produced and then.
What's the question? Sorry, production.
The question in the chat says production meaning at the time of re-entry, right?
At the time
These are not fluctuations that are entering the horizon. They are produced inside the horizon.
They are already sub-Hubble. Yeah, I'm not sure what you mean by this. Sorry.
Maybe you can check in the chat. Maybe I'm just.
I said at the time of production. You see,
okay.
They are being produced. Typically, this is considering post-inflationary processes. Okay, but you could also do it during inflation, by the way. Yeah?
Okay.
The question, Nico, I think somebody...
Yes. How is calculated raw dot when we have fixed background expansion? That's a good question. So when we have a fixed background expansion, that means that you fix your Hubble rate initially, and that will define your critical energy density. So that's why we here, I am not saying that, okay, so that this could be misleading, but I am plotting the gravitational wave energy density per logarithmic interval as normalized by the total energy density. So when we have a self-consistent expansion, this is the actual critical density. But when we have the fixed background, this is not longer true. So the omega GW is no longer true. So in that case, I will show you what you should do, because this can be changed. But this is true for fixed background expansion. This is not computing the omega GW.
Sorry, Nico, just to clarify, it's not that it's not true or not true. It's just the meaning of the denominator. It's a if you go back.
Well, yeah, it's because the omega, the definition of the omega GW is a choice. Okay.
You go back to the transparency, please.
Yes.
The rho dot, you know, in the case of fixed background, we are taking what the fields that we are simulating. So it's just the dot of the matter fields, okay, not of the universe. Okay, that's why Nico is not writing critical, because it's not necessarily the critical energy density that we are outputting, the ratio there. Okay, so you just need to be aware what is the ratio, and then you can convert it one way or another.
Okay. So now let's just dig a little bit into the code, and we can see that, for example, in order to evolve the gravitational wave equation, or actually the U fields equation, it follows a very similar manner of what it was explained. For example, if we just choose the leapfrog case, we compute the kicks of the equation, which is given by the kernel. And also we evolve the drift, which is basically the evolution of the amplitude of the U fields and the evolution of the conjugate moment of the U fields. It is very similar as the case of the scalar fields. Then in another file, we compute the kernels, which are given by the gradients of the U fields in blue, and what is the actual source of gravitational waves, which is given by the PI tensor. So this is where or a product of gradient of fields or electric fields or magnetic fields goes. So if you actually go to the PI tensor file, we compute the total tensor, which is the tensor considering all the possible sources. And then in the same file, every source has its own function. So for example, scalar singlets. Scalar singlets are basically the source of scalar singlets are a product of gradients, and it's super easy to to implement it because CosmoLattice is written in such a way that you just need to write down forward differential, which is a gradient of the field A in I direction, and gradient of the same field in the J direction, and you just multiply them, and that's how it's implemented. And if you go into the same file, you will see that it's the same done for the complex scalar fields and the magnetic and the electric fields. And it's super easy to implement it and super easy to follow from what is written in the equation and how is it implemented in CosmoLattice. And then in a slightly more complex, which is how it's done, the projection of the U fields to the actual transverse traceless fields, that the ones that we want to compute in order to obtain the power spectrum, is done in a GWS projector. And for example, here you can see we are defining what is P. Basically, this is what this function does. And this function also takes in consideration which choice of lattice derivative you are taking, and is being computed here. So K lattice derivative, depending on which type you are giving it, it computes it in different ways. So if it's 1, is the neutral derivative and is the real valued one. And if it's 2 or 3, it computes the corresponding one. And this is important because it actually, if we choose the real value projector, it will make the computation of the power spectrum easier. So that's why you can choose that. But there is no much of a difference in computing the complex or the real value ones. I think there is a question. Oh, it was related to the previous. Maybe I can answer to the end. Sorry, I didn't check there was a question. And here is where we actually compute now the product of the time derivative. And we are basically, as you remember, we want to compute this thing. This is what we want to compute, the trace of the product of these matrices minus 1/2 the trace of this. And this is where it's done. We just compute term by term the product. Like, for example, the 1/1 is being computed here. And then we use it to construct our traces. And this is where it's done everything. This is where we compute now the product of the transverse traceless tensors from the U tensors that we are evolving in the lattice. You can see how it's being computed, this part in red, the part in blue, and the part in green. And for the real projector, this is very similar. It's done in a similar manner. So it works both the implementations for both the real and the complex projector.
There's a question, Nico, in the chat.
Yes. So here, K lattice square is actually K lattice. Yeah. Yeah, for the choice of the complex momentum, yes, the K lattice square that, for example, is being computed here. You can see in line 61, K lattice square is K lattice in one direction times the complex conjugate. So yes, but for the real one, this also works. So
yeah, but in denominator,
just by default compute it like this.
Nicholas, I mean in denominator, it's then KL and then KL complex conjugated, right?
Yes.
Okay.
Yes, exactly. So it's like you can see in line 61 K lattice square. Is that what you say? K lattice K times complex conjugate K lattice.
Thanks.
And the same formula works for both real and complex value. Yep. So, and then this is basically what to answering one of the questions that if we do actually compute the gravitational wave power spectrum using both type 1 and type 2 constructors of power spectrum, and it's basically here. We are actually doing that, and it doesn't cost anything in terms of computation, doing one or the other. By default, is given the type 1, which is the one that counts literally the number of points per beam, and that's why it's here in the formula. So this is the final formula that we computing in CosmoLattice to get the gravitational wave power spectrum. You can see, and for example, to the people that was asking, when we divide this by the total energy density, in the case we have a fixed background. So what you can do is go into this file, GWS power spectrum, and instead of normalizing by the energy, the total energy of the matter fields, you can replace this by the critical energy density of your fixed background. And you just need to change that. And it will give you the omega GW for the case you want, for in this case, the fixed background. You just need to go here and change this for the critical energy density of your fixed background. And this will give you.
Or a posteriori of your simulation, you can also post-process the output by simply multiplying this amplitude by the ratio of energies, rho tot tilde over the rho critical of your background. You know, that's simple. And
I mean,
you know, the reason why we do it like this, because this is the fraction of the energy radiated in gravitational waves from your source fields. Okay, and I think that's the physics, is to understand how much energy you are radiating from your source fields. If you want to retrieve this till today, then you know to do this, you need to do this trick that Nico is explaining one way, I'm explaining another way.
Yeah, you can do both things. Like, so you just need to take into account that, for example, how CosmoLattice is done is that energies are being computed every time you compute a volume average, and the spectra are being computed in a different time step, let's say. So you just need to take that into consideration when you cannot just multiply the same file that gets you the total energy of matter fields times the whatever you got from gravitational waves. You just need to take into account that. There is okay. So I think we answered the question by Ricardo with this, and this is the last slide. So I think it ends here. And if you have any further questions, I'm happy to answer.
Nico, thank you very much. Okay, yeah. Are there more questions?
Or did we answer Ricardo? Let me make sure. So Ricardo say, see, if I have just one scalar field, it corresponds to the energy density found in the average energies file in the last column. Yes, this is the total energy of the matter fields. Yes, the last column of the average energies. Yep. Okay. So that's all. Okay. Any other question? So if you want to know maybe how to arrive to this equation, you can look at the technical note 3, and there is a slide, very simple explanation how do we arrive here, but basically it's just you write down the Lagrangian of all the possible fields that we have here, scalar, complex, scalar, and U1 gauge fields. You write down the energy momentum tensor of your Lagrangian, and then you just take the anisotropic part of the spatial component, and you arrive to this formula. I mean, you have to work on a little bit to get the electric and magnetic fields here, but you can do that. And you can do that exercise. And it's very important, the minus sign here. It can seem weird, but it's actually important that it goes like that. Okay, any other question? No.
Okay, if there are no more questions, I mean, we're happy to wait 5 more minutes, but
Yes, we will stay here.
let me remind you that tomorrow we will have, in any case, a practical session.
Sure, yeah.
Waves, which will be co-led by Nico and by Jorge, or I don't know if it's just one of you taking care of, or both of you.
No, I will be there, but mainly Jorge.
Okay, so Jorge is leading it, and Nico will be supporting there. Yeah, and this afternoon, at least in Europe, afternoon for us at 2 p.m., we will reconvene, as usual, 5:30 in India, 8 p.m. In China, with the theory on non-abelian gauge theories of the SU2, which will be led by Adrian. Good, so if there are no further questions, then I think I stop recording.